Hello everyone, and welcome to Biopedia. This week we're going to discuss another example of the impacts of climate change. This is because it's having an impact on something we would consider fundamental, the length of a day. Now, this isn't the only time in Earth's history that the length of a day has changed. About 2.5 billion years ago, a day was 17 hours in length, rather than the 24 hours we are accustomed to. Then, for about a billion years in the middle of the Proterozoic, a day was 19 hours long. The length of a day has then steadily risen from 19 to 24 hours over the last billion years. Broadly speaking, the Earth conserves its angular momentum because the planet and the atmosphere are relatively isolated from everything else by space. However, this isn't entirely true. We should discuss the forces that affect day length and which are theorized to have balanced each other out when our day length was stabilized at 19 hours for about a billion years. On the one hand, sunlight and therefore heat energy is absorbed by water and ozone in the Earth's atmosphere. This means excitation of something called atmospheric tide. We're not going to go into the physics of it all here, but the take-home message for our purposes is that forces due to the sun act to speed up the Earth's rotation. On the other hand, we need to consider the moon. Earth spins on its axis faster than the moon orbits around it. This means that the bulge created by the tides moves faster than the moon does. This ends up moving angular momentum from the Earth to the moon. The result of this is that the moon is moved into an orbit that is further away from the Earth, acting to slow Earth down. Over geological timescales, you can see the effects of this. When the moon first formed, it was only 22.5 kilometers away from the Earth. Now it's over 400,000 kilometers away. The moon is, in fact, moving away from our planet at about a rate of 3.78 centimeters per year. This is about as fast as fingernails grow. One reason for this long-term stability of day length across a billion years in our past may be that ozone built up in the atmosphere after the Great Oxidation event. This is relatively more important for the magnitude of the solar tide, as a 2023 paper calls the effect from the sun. This meant that it was a bigger force and could act to counteract the effect of the moon moving away. Moreover, lower oxygen levels and hotter temperatures make the atmospheric tide stronger. After the Great Oxygenation event, oxygen levels fell. The general idea here is that the Great Oxygenation event, followed by a later drop in oxygen levels, created this equality which meant the day length stayed stable for a billion years. In essence, the two sides of the equation balanced each other out. With prehistory covered, let's shift our perspective forwards towards the modern day and examine how climate change is impacting our day length. Melting ice in Greenland and Antarctica has meant that the angular momentum of the Earth has decreased faster than it otherwise would have. When the ice melts, it spreads across the world rather than being concentrated at the poles. I've heard an analogy before, in admittedly a different context, on the YouTube channel Kurzgesagt about a ballerina spinning faster when they tuck in their arms. However, I should say that I forget which video this was in. If I rediscover which one this was, I'll put a reference to it in the episode description. The reason I bring this up here is that, if the ice is spreading from the poles and moving out over the rest of the world, I suppose this would be like a person spreading their arms out while spinning instead of drawing them in, which would intuitively make them slower. If we extrapolate forwards in time, we may have to take a leap second off coordinated universal time by the year 2029 because of this impact. In the 2024 paper discussing this phenomenon is called a negative leap second. I should clarify that a leap second is a phenomenon similar to a leap year. Essentially, it's a correction made to the calendar by the addition of 1 second. Let's talk about leap seconds to exemplify this change. Between 1972 and 1999, a leap second needed to be added 23 times. If we count 1972, the interval from 1972 to 1999 had 28 years in it. This means that about 82% of years needed a leap second adding during this interval. However, in the last 23 years, we've only needed 4 leap seconds. This means that about 17% of years needed one, a noticeably lower figure. So, there you have it. Another example of climate change impacting our world, possibly in ways that you might not have expected. As always, thank you all for listening. Feel free to get in touch at the show's email address with any questions, comments, or topic suggestions for future episodes. Until next time, have a great week, everyone.